Well, hello and welcome to today's webcast. I'm Kelvin Ross and I'm the editor of Power Engineering International. Today's webcast promises to be extremely interesting for us all as it tackles one of the hot topics in the power industry just now, namely gas turbine efficiency. Specifically, today's event is a gas turbine owner's perspective on Turbophase power and efficiency, and we have two presenters, Steve Quisenberry from Powerphase and Gregor Kneeded of Sargent Lundy. First of all, Steve will give us an overview of the Turbophase technology, and then we'll hear from Gregor. Now, Sargent Lundy's worked with several gas turbine owners to analyse the impact of Turbophase and a host of gas turbines at varying site conditions, and Gregor will present this considerable on-the-ground experience. A little bit about both of our speakers. First of all, Steve has 18 years of advanced engineering and turbine experience, beginning as a flight test engineer for Pratt & Whitney and then as general manager with Alstom Thermal Service PSM Middle East. Gregor is a principal consultant with Sargent Lundy in Chicago, and he has 30 years experience in the energy business in consulting and operational management. Before joining Sargent Lundy, he had a long career with global power companies such as ABB and Alstom. In fact, he was the product manager for large advanced gas turbines for 5 years at ABB Power Generation, and subsequently responsible for gas turbine combined cycle power plants as managing director at Alstom for a further 10 years. So between them, both of our presenters have a broad and very deep understanding of the gas turbine market and the challenges and opportunities in it. This event is sponsored by Powerphase, which develops systems that help power plants use air more efficiently in both the storage and the production of energy. The company's flagship product is Turbophase, which is a modular system that improves efficiency, power and responsiveness on existing and new combustion turbine power plants. I'm very familiar with the Turbophase system as we've written about it very recently in PEI magazine. It improves capacity by 10 to 30% and up to 5% improved heat rate, and that's at all ambient conditions, so it's a very exciting piece of technology. This presentation is both live and interactive. You can ask questions at any time by typing them into the Ask a Question box, which you should be able to see in the presentation window. If you have a question in the course of the two presentations, just fire it off in that box, and when Gregor's second presentation is finished, we will go through as many questions as we can. So if you can keep them short and direct, that means we can get through more of them. If you need any technical help, if you can't see something, if it's not looking right, you can alert us through that Ask a Question box, and a member of our support team will work with you to get things fixed for you. PDFs of today's presentations can be found in the Event Resources section, directly below that Ask a Question area. If you're running pop-up blocking software, you will need to disable it to view this webcast. To get the best out of it, I'd recommend you also close down any other applications you might have running at the same time. You'll get the best out of the webcast then. This presentation will be available on demand within 24 hours of us finishing today, and a reminder email to all of those who have registered will be sent with a link to that archive. You can also access that from the homepage of Power Engineering International, which is, if you don't know, powerengineeringint.com. So let's begin, and it gives me very great pleasure to introduce Steve to deliver our first presentation. Over to you, Steve.
Well, thank you, Kelvin, and good morning or good afternoon, depending on where in the world everybody is sitting today. So first, let me thank Kelvin and PEI for setting this up, and Gregor and Sargent Lundy for joining us. We've had a tremendous response over the last couple years on Turbophase, and Sargent Lundy's played a big part in analyzing systems for owners and lenders with the application of Turbophase. So first, let me give you a little background. We have spoken to customers all over the globe over the last 3 years since we released the Turbophase product. ranging from IPPs to straight cogen operations, integrated water and power plant facilities in the Middle East, and global utilities, all the way down to industrial mechanical drive gas turbine owners. And the macro and microeconomics change where you are in the world and your individual situations, but there are several topics that just keep reoccurring. And so this is a good opportunity to kind of address some of those. I'm sure we won't get to all of them today, but we are available. Contact information is also provided. You can reach out to us directly. All right, with that said, we'll go through, let's see if we can change the slides here. We'll go through a little quick overview of the technology. I won't spend too much time on that, but we'll go through the applications as we apply to the different types of power stations. Address a common metric, which is levelized cost of energy, and how Turbophase fits into that, as well as just kind of a generic value proposition, and then some specific industry feedback. So with Turbophase, and why we created Turbophase, right? This was a product we invented in 2012. Patents were complete in 2013, and our first install was in 2014. But the whole genesis behind Turbophase was to allow more renewable penetration into the grids and using your existing combined cycle and simple cycle gas turbines to support that renewable deployment. And that is, they have to get more flexible. Today's combined cycles, start times are long. They are difficult to ramp. The start cost to owners is high. And when you combine that with the simple cycles, 10 minutes is not fast enough from a start time. So we brought Turbophase to basically provide the benefits of a flexible peaking simple cycle power station at battery speeds, but at combined cycle efficiencies. And so that was the whole genesis of why we started down the path with Turbophase. And where that addresses the need is this very simple slide here. I know this is oversimplified, but as we all know, your gas turbine is a fixed volume mass density machine. And what I mean by that is it gets hotter, density goes down of the air, your power goes down proportionally, almost linearly. And so as nobody obviously runs a gas turbine year-round on ISO day, 15C, 60% relative humidity, and sea level, I challenge anyone to find a power plant even located at those specs, but those are the design specs. And so when we apply Turbophase to the gas turbine, we're replacing that air with naturally created air to generate more power out of the gas turbine and to improve the efficiency of the underlying gas turbine asset. So Turbophase works when your power is needed the most. Demand across the world also grows with increasing temperature as both industry users and household users are requiring more electricity. So when the gas turbine performs its worst is when you actually need the most power, and also tends to, if I overlay this with wind in most of the world, you also get the wind stops blowing as it gets hot. And so as you integrate renewables, it's also the point in which you have the worst wind production, and then you can balance solar into that as well. So as a intermittent resource. So Turbophase is there to make the gas turbine respond to that changing ambient conditions so that we can actually have a baseload consistent output instead of a variable output with the weather. So a quick look at what inside the Turbophase module. I think a lot of people have seen the outside of the blue box, but the inside of the blue box. So inside the unit, we have industry-leading world-class components that we assemble. As I like to say, we don't actually manufacture these components. We purchase these components. What we have patented and what we put out to the marketplace is a process, which is using a fueled source to compress air and then inject that compressed air into the gas turbine. And so inside the module, in this picture here, you actually see an MTU Series 4000 engine. We also use a Caterpillar engine, and you see a SIA compressor, which is made in Korea. We've also used a Hyundai and a Samsung compressor. These are all purchased world-class components. The thousands of them are in existence with millions of fired hours on them, and we're just using them for a unique process. Typically, you see these engines in marine applications as well as in genset applications. The compressors are used in everything from instrument air compressors to medical grade dry air, because they are an intercooled compression cycle, which removes all the humidity from the air. A little side note, we make about 3 liters a minute of clean, fresh water when we compress the air. All right, so the outside of the box, what we mentioned and Kelvin mentioned, it's a modular system. What you see here is an install in Southeast Asia that was recently completed. And the purpose of these pictures is to show you the box is delivered in 2 lifts. It's fully assembled, fully factory acceptance tested. And when it's delivered, it's the major kit that you see on the top right, and then a roof skid that's lowered on the roof. It's got 6 connections, and the 2 units in this picture are put together in a day. Prior to arrival, it is pouring some civil concrete works and running the pipe connections for the fuel and the air and the water. But assuming all those are done in advance of arrival, the box itself is delivered and put in place in a day. All right, so to focus on this webcast of where we're adding value to the owner's perspective across the different types of plants. And what we see can be broken down into kind of these 5 categories of baseload, cyclic, peaking, standby, and then ancillary services. And depending on which market you're in and whether it's an open free market or whether it's a utility basis, these may have different macro, micro economic requirements. But in general, your power plants operate in one of these 5 modes. And where Turbophase applies is whether it's a base load plant and we're generating more energy, more kilowatt hours at the most efficient plants, we're able to do that and lower the energy cost, the cost of generation of that facility, because the cost of Turbophase kilowatt hours is lower than the base cost of the power station. In a cyclic mode, a plant that runs, let's call it, 8 hours every day, 5 days a week, or starts in the evening. From that standpoint, the ability of Turbophase to bring 50 megawatts into a 500 megawatt facility and use that 50 megawatts to cover the intermittent spikes and to backstop the renewable penetration allows that base load 500 megawatt facility to stay online at a higher efficiency longer, and use Turbophase as the ramping or peaking application in that cyclic environment. That also allows for better operational flexibility in a multi-gas turbine environment, where in a power station, let's say with 4 gas turbines, instead of bringing all 4 on, you may bring 3 plus Turbophase. And that allows to reduce start costs. In addition, then, as into the true peaking environments, those of you that run, 2 hours every other week, just to support emergency needs or to backstop renewables, the challenge there is your start times. If Turbophase is applied to your combined cycle assets that run more and is literally not running, it is available to immediately bring on versus a 10-minute start simple cycle, say LM6000. A direct example would be to put 50 megawatts of Turbophase into your F-class combined cycle power station, having it there on standby, starts in 1 minute, and provides 50 megawatts in 1 minute at combined cycle efficiencies, instead of starting that LM6000 or that SGT 800 or something of that nature in less than 8 to 10 minutes, and having the start costs and the start emissions associated with starting that unit, and then also having to build that peaking power plant to begin with. So we can basically direct offset those peaking power stations. And then ultimately standby, Turbophase, as I mentioned, the engines are typically used as gensets. we have the ability to put a black start 2.5 megawatt generator on our unit, whereby the Turbophase module can be used not only to make air, but can be clutch out the compressor, and we can clutch in the generator to make 2.5 megawatts of black start power per box. And this allows us to be used for emergency standby or black start of the facility. And then ultimately, ancillary services here in the state specifically, the regulation, meaning frequency response up and down. Turbophase is very quick. We can change the power into the gas turbine as fast as we can move a control valve and as fast as the gas turbine's fuel system can respond. And so with that, we're able to be put into an AGC mode, an automatic grid control mode, and let Turbophase just follow a grid demand signal. That allows the gas turbines to stay fixed at base load and allow the Turbophase modules just to move the air production up and down. So across all those methods, across all those needs of power plant owners, we see an application for Turbophase. What I didn't address in here was the mechanical drive customers. We have several, especially in the oil and gas industry, where that gas turbine is being used to drive a compression cycle, especially in like an LNG train or a polypropylene or cryogenic process. And in those same things, as we make more electricity or kilowatt hours, we're also making more horsepower, shaft horsepower, and that allows those compression cycles to put more product down the pipeline. So whether it's mechanical drive or electrical production, and whether or not you're peaking all the way to base load, there's an application that fits. I added these slides in here mainly for you all afterwards to review, but what I want to show here is 50 or 60 hertz. It's the same blue Turbophase module. Nothing changes about the module. We make a certain amount of kilograms per second, pounds per second of air production at a certain pressure and temperature. And when we apply those to different gas turbines, we are targeting 5% mass injection. The reason we target 5% is most of the owners will recognize that 5% is a common number used by your OEMs for steam injection, wet compression, and as well as NOx abatement water for mass. So all your gas turbines are designed to handle a 5% influx of mass, typically done by the OEMs with water. We're just doing it with dry, clean air. So these numbers relate to the power that you can achieve on each frame, 50 or 60 hertz. The efficiencies are a function of the heat mass balance of that particular site. And our team does those routinely for customers where we come in and analyze your heat mass balance, and we provide a efficiency target for you. On these charts, what you'll see is a number of modules increase as the gas turbine gets bigger. By us making one common product, it's an economies of scale discussion. We're able to make a common product that allows us to keep parts common, keep supply chain common, and all that keeps the cost down. One of the metrics you see that I know most of our asset managers we deal with is a levelized cost of energy when looking at new generation. And this really comes from the utility perspective. And so when you're looking, a common metric is the Lazard indices. This happens to be the 2015 indices that's shown on the screen. And what it does is take a constant debt to equity amount, constant interest rate, fuel costs are held constant, and the different technologies are analyzed at a dollar per megawatt hour basis. And when we do the same, when we run the same metrics with Turbophase over the same life cycle costs, what we find is the operating costs per kilowatt hour or megawatt hour are about half of what your combined cycle is. And so this allows us to be able to show to customers what the operating costs and the net benefit between the capital and the OPEX and the fixed O&M costs are for the product. And these take into account net power. I think one of the questions that popped up a little earlier while I was speaking was about how much power is consumed by the module. We're producing 6 to 8 megawatts of power on the gas turbine. We're consuming 35 kilowatts. So to repeat that, 6 to 8 megawatts on the gas turbine per module, we're only consuming 35 kilowatts of electrical power. And in that, it makes for a very flexible, easy install. Our desire here is to burn gas for more gas-fired generation, right? So we don't want to consume electricity or water. So we consume zero water and minimal electricity. And what results in this is a generic 10 to 30% more power, 3 to 8% fuel efficiency on the gas turbine. And as I just mentioned, we're about half the cost of a combined cycle per megawatt hour. And the biggest one is the most flexible solution. As unlike a turbine upgrade or something that's specific to your gas turbine, this is a power plant solution. When we install Turbophase into the power station, we connect it to all the gas turbines in the power station. We can direct that air to any gas turbine that is operational. So we have clients where they may have 4 gas turbines, that 3 of which run. One's in a hot standby, and they rotate every week, which 3 run. This allows them not to have to upgrade all 4 turbines, but upgrade just the power station with Turbophase and direct the air where they'd like. It also allows them to offset planned shutdowns. So kind of to summarize a few of the points here, it's an output increase, and I think we've done a lot of discussions in the past around how air mass flow increases the output. By adding more mass, the gas turbine adds more fuel, and since we add a constant amount of mass at all ambient temperatures, humidities, and elevations, it doesn't matter if the gas turbine is sitting in Mexico City at 6,000 feet elevation, or is sitting in the Saudi desert at 50 C ambient, or in Indonesia at 100% relative humidity at 28 C. We are independent of all ambient conditions. And the gas turbine turns that air into electricity at the same rate. Since we make constant air, you get constant output. And then with the fast response, as I said, we're 1 minute to start. Once we're online, we're as fast as we can move a control valve, so we're milliseconds. And that allows us to implement essentially the spinning reserve needs of the utility without actually spinning. And so therefore we're consuming the need for that spinning reserve without actually burning fuel. And as I mentioned, we don't consume any water. And from an emission standpoint, we are a dry pre-mixed combustion recip engine, making about 42 ppm NOx. If a customer needs sub 5 ppm, we put an SCR on the unit. And then all this results in improved efficiency. And one of the things that comes up is always about the gas turbine maintenance. We make a different amount of megawatts per module per gas turbine based on firing temperature. Right? A B-class gas turbine has a lower firing temperature typically, and pardon for those that think in Celsius, I think in Fahrenheit. Call it a 2055 firing B or E class gas turbine compared to a 2400 firing F class compared to a 2650 firing H class gas turbine. The higher the firing temperature, the more kilowatts per pound per second of air you make. So we make the same amount of air. The higher the firing temperature is, the more kilowatts per pound per second of air you receive out of it. But the key to this is that we don't change the firing temperature. So since the firing temperature is unchanged and we're not injecting any water or steam, there is no maintenance penalty to the gas turbine. Just if you look at your OEM factor fired hour calculations or equivalent operating hour calculations from your OEMs, you'll notice that there is zero effects of ambient temperature. There's nothing in your calculation for your planned maintenance that accounts for changing ambient conditions. And changing ambient conditions result in changing mass flow. And therefore, from that, you can understand that mass flow, as long as firing temperature remains constant, has no effect on your turbine. And then obviously with all this, the return on investment. This is a business. We're all trying to make power. We're all trying to turn that into the lowest cost of generation. And we believe we are the lowest cost of generation available on the market. And I actually had one of our board members the other day, who is a non-technical individual, said, guys, I get it. Air is cheaper than fuel. And what is meant by that is we make air more efficiently than the gas turbine makes air because we're an intercooled compression cycle. If you go back to an enthalpy diagram, TS diagram, you will see that intercooling process is more efficient. And when we do that, we make air, and adding more air is cheaper than putting in more steel to burn more fuel. And with that is our air is being produced, like I said, about 35% more efficiently than the gas turbine makes air. And this allows us to improve the grid efficiency and lower the cost of generation. Interesting enough, that board member, which was our former Chief Technology Officer of GE Corporate for about 20 years, a gentleman named Dr. Mark Little, who recently joined our board, basically coined that phrase for us. And then just to address the operational efficiency, as I talk to different utilities and different, I would say, government-owned grids around the world, there is a unique perspective from the utility point of view, which is to add power to your most efficient assets at combined cycle efficiencies and reduce the inefficient simple cycle CT hours. So if you are going to go put 100 megawatts of Turbophase into the grid, that same 100 megawatts can offset 100 megawatts of simple cycle power. And that 100 megawatts at 55% efficient versus 100 megawatts at 35% efficient is a 20% efficiency change of those kilowatt hours produced. In addition to lowering emissions by reducing startup cycles, and also lowering emissions in tons per MMBTU input because the efficiency improves. And all this helps with lowering the cost of generation, lowering O&M costs, startup costs, maintenance costs, et cetera. And so when you start talking about a large fleet across a grid instead of just a particular power station, this becomes game-changing. This becomes, when we start talking about 1% in a combined cycle efficiency is huge, which is one of the OEMs recently stated. Well, 20% across the fleet is an order of magnitude change. And that all goes into allowing renewables. We all agree that renewables are good, renewables are needed in the power industry, and as they bring into the grid, it's the fact that the combined cycle gas turbines now have to start acting in a more flexible manner. And Turbophase makes that gas turbine have a much larger range of fast response and increasing that flexibility both up and down to be able to support that renewable penetration. And then finally, guys, just the last bit here, and then I'll turn it over to Gregor. The industry adoption. As we place units into the field and speak to owners around the globe, there's questions to their maintenance providers, the EPC developers, the owners and lenders, and the insurance providers. And with the maintenance providers, a little background on Powerphase. I think a lot of folks have heard of our previous company, which is PSM, which is owned by Ansol these days, which is the largest third-party provider of parts and service. That was started by the same management team here at Powerphase. A gentleman named Bob Kraft started that company in the late 90s. The company here at Powerphase is all turbine designers by background. We do a lot of due diligence into understanding how Turbophase affects your gas turbine. And in doing so, we also understand how it affects your maintenance agreements. And there is zero impact to your maintenance agreements, technically. Commercially, you'll get different responses from the different OEMs. EPC developers, what's been interesting recently is we've supported a lot of new projects, greenfield bids, where the OEM gas turbines don't fit a certain range. For instance, one customer was looking for a 1,050 megawatt power station, and the desired gas turbine arrangement provided 1,000 megawatt combined cycle facility. And so the developers came to us to supply the extra 50 megawatts. And so the EPC and developers are looking at it from twofold: one, to fit a missing void, and also when you start integrating Turbophase into a greenfield project, there are certain things we can do with our waste heat that allow for a better optimized bottoming cycle, and resulting in about 0.5% of combined cycle efficiency improvements off the bottoming cycle, and displacing duct firing and inlet conditioning and some water consumptions on the D-min cycle. Next is the owners and lenders engineers. Obviously, Gregor from Sargent Lundy is going to talk about this. We don't have a single customer that doesn't request a third-party technical due diligence, whether it's the owners or the lenders. And Sargent Lundy's been a big part in doing that for a lot of customers. So have many other A&E firms. And that's been really positive. And then the insurance providers, we've gone through with clients as their insurance providers come on board, whether it's AIG or FM Global or others. We've done the due diligence. Most of the questions have been around the controls integration and fire detection and suppression, which inside of our module there's a complete detection and suppression system. And so along those lines, we've gone through those and had no change to insurance premiums with every owner or lender we've dealt with. So these are all part of adopting new technology into the market. Obviously, more references in the ground make it easier for the next folks to move forward, but this due diligence is being done from all these different parties. And so what I'd like to just end with is I'll turn this over to Gregor. The contact information is provided here. We will follow up with all the individual questions asked if we don't get to them on the webcast today. If there's specific questions, you can feel free to reach out to us directly. And kind of with that, Gregor, I'll turn that over to you to go through the slides you have from Sargent Lundy.
Thank you, Steve. This is Gregor Gnedig speaking for Sargent Lundy. I'd like to also thank Calvin for the introduction, and I'd like to greet everybody who has joined this webinar. Sargent Lundy, we are an engineering company located in Chicago. We have offices in Canada and Abu Dhabi, in Saudi Arabia, and in Baroda in India. We are privately held, 2,400 staff, out of which we have about 1,800 engineers. And just at the bottom there, we are ranked in the top 5 in the US and top 10 worldwide in regards to the Engineering News Record magazine ranking that they introduce every year. The importance here in regards to our involvement in the project is that, as Steve has pointed out, a lot of the owners of these and operators of the power plants, they require an independent assessment of the risks of new technology that they introduce in their power stations. And that's where we come in. I have here a slide that our capability at Sargent Lundy clearly cover the entire time frame from the development of a project through the construction phase into the operational phase. Most of what we see here with the Powerphase and the Turbophase implementation would be during the operations phase. Most of the time, these are stations, power stations that are already in operation, where the owners have a requirement for additional power, and they then basically decide to look at Powerphase and at the Turbophase technology, and they come to Sargent Lundy to get an independent assessment. Typical due diligence, technical and financial due diligence that Sargent Lundy would be required to do in the context of a Turbophase project would be to look at how does it impact any of the aspects that are related to the power station. Now, what I show here is all the aspects that are related to due diligence. Clearly, when we come to implementing Turbophase, we wouldn't look at all of these issues. We would typically look at the technology and the design. We would look at the permitting. Are there any changes to the permitting of the power station? How does it impact the operations? And we would also look at the financials, meaning how does it impact the bottom line of that power station. We have completed more than 400 of those due diligence projects over the years. And again, the market that we are covering is Southeast Asia, it's the Middle East, it is Africa, Europe, all the way into the Americas. Obviously, a lot of the market that we cover is in Latin America. But we have seen interest for Powerphase in all regions of the world. And clearly the need there the need is very similar for most of these owners. In regards to the Turbophase installations, and this question has been asked repeatedly, currently there is Morris Station, which is in the United States here in Illinois, which is in operation where Turbophase is installed, and there are demonstration units in Saudi Arabia where this technology has also been installed. Sargent Lundy has been involved in both of these projects, and in addition, we have been involved in a number of due diligence reviews for new clients of Powerphase that basically require an independent assessment of the risks associated and the opportunities associated with this technology. Now, currently, we are looking at multiple projects, new project opportunities for Powerphase in Southeast Asia and Latin America, where Sargent Lundy has been requested to carry out this due diligence. Now, as Steve has very well explained, it's a power augmentation method, Turbophase, and clearly has a huge advantage in regards to warmer ambient conditions, where all gas turbines as constant volume machines show a reduction in power output that can be up to 5 to 10%. And clearly, this is the opportunity where the Turbophase technology allows that some of this capacity that is reduced can be recovered. And if we go to the next slide, we basically, as Sargent Lundy, have confirmed that the inclusion of Turbophase will result in a better heat rate in simple cycle. The reason is the gas turbine typically requires 2/3 of the heat input to be used to drive the compressor, and 1/3 of the thermal power is actually only available as the electrical power at the generator. And since this air is compressed externally in an external compressor, you have a substantial, significant efficiency advantage for that additional megawatts that are being generated in the turbine by that air being compressed externally. And in combined cycle, where again you have the advantage with the increased mass flow in the turbine that you also, this going into the heat recovery steam generator, will actually increase the steam flow and thus also the steam turbine capacity. So you have a double impact here in regards to increasing the gas turbine power output as well as the steam turbine power output. Last but not least, many of the owners and operators of gas turbine power plants in simple or combined cycle require quick startup and quick ramp up capability, and with Turbophase technology being on hot standby, air injection can begin very, very quickly, and thus also the power station overall can follow the ramp rate of the gas turbine very quickly and provide additional power output. Now, we have seen most of the interest when we are being contacted is from owners of frame-type combustion turbine. They are typically larger than 20, 25 megawatts, and the reason there is these units are obviously they're very robust. There's many of them out there, thousands of those turbines. Many of them get older, have some deterioration. As those units get older, they might lose as much as 2, 3, 4, 5% of the power output. And therefore, owners and operators are looking at means of recovering that deterioration, and Turbophase is in that area of 10 megawatts, 20 megawatts that they can provide, depending on the size of the power station. As we said, it's about 10%. And clearly something that owners appreciate as an option. Now, when we are being involved, the owners and operators are quite concerned about what does it mean to the availability of the plant, what does it mean to the lifetime of the plant, what does it mean to the maintenance of the plant. And in our assessment, clearly this is something where the gas turbine is designed anyway for the larger mass flow at lower ambient temperatures, and therefore the additional mass flow that is being introduced, 5%, is really not changing the maintenance or operation of the power station. It does not increase. Obviously, you have a small additional maintenance due to the reciprocating engine that is used to drive the external compressor, but this is a fairly small unit, and thus it's not a big difference. And on the operation side, we have assessed that there is no additional risk to those units as it stays within the range for which the gas turbine is designed in any case. Here we have a summary just reflecting what most clients that contact us are looking at as an alternative. When they look at Turbophase, they also say, well, we could do inlet chilling, we could also do peak firing, or we could do increased duct firing in the HRSG in the case of a combined cycle. And our assessment there is that all those technologies have advantages and disadvantages, but if you look at some of those items that we list on that page, you can see that Turbophase compares quite well because it's a significant increase in plant capacity. It's a quick startup time and a very short outage. If you take, for example, inlet chilling, especially if you have thermal energy storage associated with inlet chilling, some tank that might take up to 6 to 12 months to install, whereas Turbophase obviously can be installed in a much shorter time period. Also, capital cost is quite competitive in regards to comparison to inlet chilling. In regard to peak firing, most people who know gas turbines know that you pay a price for peak firing the turbine. The maintenance regime changes rapidly. You have a lot more maintenance. Every peak hour might count as much as 20 operating hours at base load. So again, it is something where you have a smaller performance benefit if compared with some of the other technologies, and you have the additional plant maintenance that can be quite expensive. In regard to the increased duct firing, which really is only available obviously once you have an HRSG in combined cycle operation, you have the advantage of the quick startup time, but again, if the HRSG is not designed for duct firing from the startup, from the very beginning of the design of the power station, it's quite difficult to implement duct firing. It requires substantial modifications to some of the equipment, and also the heat rate, the efficiency is impacted by duct firing quite negatively. And therefore, in this overall comparison here, we believe that Turbophase technology rates quite well, has a lot of advantages and very few disadvantages if you compare it with some of the other technologies that are available. Now, many of you probably would like to hear more specifics in regard to well, how many megawatts exactly did you see in station A or B? What was the cost advantage? Most of our work is confidential. Our clients do not want us to basically present these numbers to the outside. These reports that we prepare as independent engineer are tied to those confidentiality agreements that we sign, and therefore we will not and cannot really share specifics. But very clearly, all the projects we have looked at, and there are numerous of those projects, have shown payback periods that are quite short. Typically, I would say 2 to 5 years, which is quite good for given the opportunities and possibilities associated with the technology and the very limited risks and disadvantages associated with the technology. And therefore, we clearly see the technology as a feasible option to increase the gas turbine power plant capacity at very low risks, small heat rate penalty, and relatively low investment costs. So we have had an opportunity to give positive feedback and assessments to many of the clients that we are dealing with. And again, I guess that was one of the reasons why we have been asked to represent these companies that own and operate Turbophase and that are interested in installing Turbophase technology. And we have been in a positive situation that we have been able to support the technology in regards to an independent assessment associated with all the advantages, disadvantages, risks, and opportunities that are associated with new technologies. And that brings me to the end, and will also give us some time, 10-15 minutes, to answer some of the questions. And I'd like to hand over to Calvin to kind of see how we're going to continue here with the questions. Thank you, everybody.
Thank you, Gregor. That was great. And thank you, Steve, for your presentation. They were both fascinating, some really impressive statistics there. Steve used the phrase game-changing, and I think it's hard to argue that the technology is anything but that. We've had a huge number of questions come in. We're going to try and whiz through as many as we can, but we won't get to all of them. But remember, as Steve said, his contact details were at the end of his presentation, as are Gregor's at the end of his. So if I don't get to your question in the next 10 minutes or so, 10, 15 minutes, then do get in touch with them directly and they'll deal with them. So we had a lot come in for Steve as his presentation was ongoing. So Steve, will probably take about 3 or 4 to you, and then we'll switch to Gregor because his are coming in. So first question for Steve is, Steve, you touched on the OEMs towards the end of your presentation. What do the OEMs say about Turbophase?
Well, that is I would say a very open-ended question. It depends on many situations. One, which customer is asking the OEM, meaning is that customer a large, utility that has buying power, or is it a small IPP that is not treated maybe as so well by the OEMs? And it also depends on which OEM. GE obviously has the largest market share, and then Siemens and Mitsubishi, Doosan, PWPS. And so it depends in that order. But in general, what you find is as the technology discussions occur, as you have the third-party independent engineers, it quickly becomes a non-technical issue and becomes 100% a commercial discussion. And that drives also whether or not there is an offering from the OEM for a turbine upgrade. Obviously, the OEMs would prefer to sell you their turbine upgrade. But in general, we are speaking to all the OEMs in very open discussions. We have supported studies by all the OEMs, and recently we signed an agreement with PWPS for application of Turbophase on all their FT8s, whereby we are jointly offering an output, efficiency, and life increase of turbine parts. And PWPS is a MHPS group company, obviously owned by MHI. And so the OEMs differ, but there are some positive movements with the OEMs, and we're excited. We developed this to work specifically with the OEMs. We do not, this is not a competing product. It is complementary to all turbine upgrades. the higher the firing temperature, the more power you're going to get out of Turbophase. So we like customers that want to do both.
Okay, great. We're staying with you, Steve, this next question, which is asking what modifications to the turbine or turbines are required to accept the compressed air from the Turbophase system?
Sure. Well, nice about our OEM friends. There are connection points on every gas turbine that are either not used at high part load or base load applications, or are just simply blanked off for other purposes. So whether you're going from like an LM6000, where there's literally a port that's used for the cabin bleed air on an aircraft, right? Because it's a flight engine, which is not used on the ground, we tie into that port. On a GE frame machine, there are inlet bleed heat systems in the compressor discharge casing that we can tie into. On the Mitsubishi Siemens, I should say Westinghouse frames, there are turbine air coolers, rotor air coolers that we can tie into. Obviously on the Alstom, 13E2s, GT2426s, there are IBH systems we can tie into as well. What makes it easy is we're not having to cut a hole in the gas turbine. We are literally tying into a pipe. Typically, for all of our installs, we have been less than a 3-day tie-in. So typically we do this tied to a bore scope inspection or plant maintenance. We do not take an outage for our system.
Okay, interesting. And do the modules operate only on gas, or are there applications for automotive diesel oil or other types of fuel?
Sure. We have essentially the only change in our box is whether I put a gas or a spark ignition engine in them, or I put a liquid fuel or compression ignition engine in them. And we buy those engines, as I mentioned, from MT or Caterpillar. And so we do offer them in diesel. Our very first unit we built was a diesel unit. So we do both. And so if a customer is running on, I would say everything from LFO to HFO to bunker C or crude, there are engines available to run them. If you can run a genset on that fuel, we can run Turbophase on that fuel.
Okay, cool. We're sticking with you, Steve, because this is one that came in during your presentation, and it is. Hang on, I've lost it now. It's on a combined cycle.
Was it the one on the bottoming on the steam production?
Yes, that's it. Yeah, how does it affect steam turbine that's running on a Hersig? Yeah.
Sure. Well, this is an interesting question. We do a lot of heat mass balances for people. These days, a lot of the power stations obviously are combined heat and power, and there may be some steam off takes. As we put more mass into the gas turbine, as Gregor mentioned, that increases exhaust energy and makes more steam. We did a study for one of the IWPPs in the Middle East that is essentially a water plant and is looking for constant steam production to make water. And they're using duct burners, supplemental firing, to move the amount of steam energy up and down. And then the electrical production of the gas turbine is just there for is following the grid, right? But they're a constant steam plant. And because they're using duct burners, which are the most inefficient, they're very good at what they do, but they're very inefficient, 11,000, 12,000 BTU per kilowatt hour heat rates. By offsetting that with Turbophase, we were resulting in a 1.5 to 2.5% IWPP CHP heat rate improvement. And so those steam plants, those are very specific heat mass balances, but that's what our team does. And so if there's a specific question on one of those, we will be glad to analyze a plant for you.
Okay, great. We'll switch to Gregor for a question now, and the question is: how do you see the growth of renewables impacting combustion turbine related technologies such as Turbophase?
Right. Now, what we have seen is that with the intermittency of wind and solar and other renewable energy sources, there is obviously the need for the base-loaded units like combined cycle power stations to ramp up in case that the renewable energy is not available. And clearly there is something where an additional 10%, 5 to 10% power output that Turbophase can provide is something that becomes high value. And therefore, we have seen an increased interest by a lot of owners and operators of power stations to look at how can we generate additional megawatts, additional power output. And therefore, we have actually seen an increased interest associated with the growth of renewable energy for peaking power stations, for additional megawatts like Turbophase can provide. And we therefore think it's an additional opportunity for the technology.
Great. Okay. So we'll stick with you, Gregor, for this next question, which is asking if you could explain any of Sargent Lundy's investigations into Turbophase's potential impact upon surge line operation or store conditions, which could damage the gas turbine. What control mitigations have been included to prevent problems such as these?
Right. As I mentioned earlier, these turbines are constant volume machines where with the temperature, the air temperature, you obviously have different mass flows, and clearly all those turbines are designed for higher mass flows at lower ambient temperature, and as the ambient temperature increases, the actual mass flow that goes through the compressor is massively reduced, and therefore you basically are never outside of your design conditions when you when you switch on the Turbophase system. You're just basically going back to the design case of the turbine. Therefore, we have not seen additional risks associated with the surge margins. Let's also clearly emphasize that a lot of the heavy-duty older turbines are designed with substantial margins on the surge margins, and therefore it is really not an issue that we have seen causes concern for the turbines.
Okay, great. If we just switch back to you, Steve, the question is, how many installations with F-class gas turbines have you done?
Sure. So the first F-class install was in Saudi Arabia, 7FA .03 DLN 2.6 with a Mark 6E controller in simple cycle. And that was the first one, and that was done to obviously show the client in that region that the Turbophase, which is designed as a 30-year industrial piece of equipment, operates up to 55C ambient conditions. Subsequent F-class installs, we currently have 3 in process, which, because they're not commissioned, I can't share with you where they're at, but there's 3 more ranging from GE and Siemens equipment.
Okay, cool. And one here on environmental emissions. How does Turbophase impact environmental emissions? Does NOx increase with Turbophase?
So with that, it's a good question, and especially for folks where permitting is a concern. So the ppm value of NOx, CO, SO2, and particulate matter does not change in your gas turbine. The combustor, as Gregor's mentioned, is designed for a larger mass flow. We're just adding mass, keeping firing temperatures the same. Now, what you do have is the emissions of the recip engine, right, inside of our Turbophase module. And depending on where you are in the world, for instance, here in the U.S., that means that recip engine has to be listed on your Title V emissions permit. And our units themselves are 42 ppm NOx, which is that is untreated. We can treat it down to sub 4 ppm.
Great, fantastic. And I'll just hop back with a question for you now, Gregor. And the question is, how does Turbophase impact compressor surge margins of the combustion gas turbine?
Well, we covered some of that, obviously. That is clearly a concern of quite a number of owners and operators, and it's something that we look at carefully. But clearly the turbines are designed for the lower ambient temperatures with the higher mass flow, so all you really do is, with the implementation of Turbophase and the use at higher ambient temperature, you bring the turbine back for what it is designed for, and therefore we have not seen a negative impact in regard to issues like surge margins for those units.
Okay, great. Now I'm just scrolling down to the next question. Let me just find out when I asked this one. This was an early one for Steve. Are the benefits of Turbophase dry air injection constant over ambient conditions?
Yes, it's a good question. So as I mentioned in the presentation, we make a constant amount of air. So the way we've designed our Turbophase module is our compressor has inlet guide vanes to open up to support changing ambient temperatures, and our engine has turbochargers on it, which allows us to keep a constant horsepower. And by keeping horsepower constant and the mass flow constant to our compressor, we make the same air. That same pound per second or kilogram per second of air makes the same number of kilowatts in your gas turbine. So we are constant across ambient temperatures, constant across humidity, and constant across elevation.
Okay. So, and another question here. Staying with you first of all to answer it, Steve. So Gregor's presentation on one page said that the Turbophase technology adds, and we're quoting now, a small heat rate penalty, unquote, while Steve's presentation says there'll be an improvement in the overall heat rate by using Turbophase, and the questioner is asking if you could elaborate and explain this.
Sure, I'll start on my end and then Gregor can follow. The heat rate for the power station is very dependent on the power station. In simple cycle, since we're making air more efficiently, we're typically a 5 to 8% improvement in simple cycle. In combined cycle, we tend to be 0 to 1% improvement, depending on how the plant is operating, depending on whether some of the steam is being taken off for other applications, or if it's a true combined cycle. So that tends to be where we are now. The one first site we did in Chicago was a small heat rate penalty to the power station, and that was being our first modules. We did not make the same amount of air out of that module as we do today. We have increased the air production of the module by over 30% since we've installed those units using the same fuel flow. So I'm assuming that may be where Gregor's point is coming from.
Okay.
Yep, that's correct. I confirm that.
Okay, fantastic. Well, there's still a huge number of questions that come in that we're not going to get to, but I would encourage those people whose questions we haven't got to get in touch with either Gregor or Steve, and they will deal with all of those questions that you've sent in. We're now over the hour that we had, but it's been a fantastic session. I've really enjoyed it and learned even more about the Powerphase technology, what it does and how it does it. So on behalf of Power Engineering International and Penwell Corporation, I'd like to really thank today's speakers, both Steve and Gregor, and our sponsor, Powerphase, for today's presentation. As I mentioned before, that presentation will be archived within 24 hours of now, and you can find it at our homepage, of Power Engineering International homepage. Also, just quickly, Steve mentioned in his presentation, he had a slide on a deployment in Asia, and the article that I referred to earlier on at my opening today's session, that article is all about the Turbophase technology in Asia, and you can find that in the most recent issue, the September issue of Power Engineering International, which you can also find on the homepage if you wanted to read some more. So yes, you can find this presentation on our homepage. Those who have registered, you'll get a reminder email with a direct link to that archive. So all that remains for me today is to again thank both our presenters. Thank you for everyone listening for joining us today, and we look forward to serving you with more webcasts in the very near future. Thank you very much.